Okay, gang, so we've made it full circle. We're now going to figure out what the exact area was under that problem that we started with at the very beginning, right? We did the upper sum, we did the lower sum, then we talked about, well, how many triangles do you need to get the exact area? And we determined it was an infinite amount. We discussed the formula to find the exact area. So like I said, we've come full circle. We're now going to find the exact area, not the estimate, but the exact area using rectangles. So just to review real quick, we decided that the exact area fell somewhere in between the lower and the upper sum. Those are the numbers we calculated. And now let's find out what the exact area is of under this curve. Okay, so I wrote down some stuff here. Just remember that this is the function. We're going from this coordinate to this coordinate, and I'm now going to talk you through how we do this. So the first thing you want to do is calculate delta x. That is the width of one of the rectangles. That is the width of one of the rectangles. So how you do that is it's the length of the interval over n. So like, for instance, some people get a little confused with this. So the length of this interval would be 1 minus 0, right endpoint minus left endpoint. And then in this case, I wanted 4 subintervals. So this would have been 1 minus 0 over 4, or 1/4, which is why I came out with this. But when you do the exact area, you actually want to leave the amount of subintervals as n. You want to keep it generic because later on in the problem, you let n go to infinity. I know that might make you uncomfortable because it's abstract and weird looking, but again, when we don't want to, we want to keep that general so that we can let it go to infinity. If I tell you on the test the exact number of subintervals, that's when you can put it in. But when you're going for the exact area, it's got to stay as n. So here I am doing it. So the same problem, we know that the right endpoint is a 1, the left endpoint is a 0. So that's the length of the interval, 1 minus 0. And again, keep it over n on the bottom, for exact area. So length of the interval, how you find that again is the right endpoint minus the left endpoint. So in our case, it was this. All right, the next thing you want to figure out is x sub I. So you can think of x sub I as you iterating across the bottom. So this would be my first x, x sub 1. This would be my second x, x sub 2. This would be my third x, x sub 3. This would be my fourth x, x sub 4. This would be my fifth x, x sub 5. Okay, so it's like that. It's x sub I because it's the particular x you're at in the iterating across the x-axis, or wherever you are iterating across. So how you do is you have to figure out where you're starting and then add the difference to get to the next point. So in our case, we started at 0, but we could have started at 3/4 or a half. We could have started somewhere else. We just happened to start at 0. So this is where you start, and then the delta x allows you to jump to the next point, right? Because if I'm here, for instance, I have to add 1/4 to get to here. I have to add 1/4 to get to here. I have to add 1/4 to get to here. So this is you adding the 1/4 however many times, maybe, you know, to get to this point here, I have to add 1/4 1, 2, 3 times. So this is how many times you've added the 1/4 to get to the next point. So here I am doing it. Again, my left endpoint was 0. I started at 0, not at a half, not at 3/4. I started at 0. I have to jump abstractly 1 over n to get to the next point, and how many 1 over n's I've jumped to get down across the horizontal, right? However many of those I have to do to get across here. All right, so this is a big I versus this one, which is a subset. So this one is like a name, my first x, my second x, where this is a multiplier. So like delta x times 2 or delta x times 3. This is a multiplier, not a name. So 1 over n times big I, not little I, big I. It's just easier for me to write it as I over n. So that's what I wrote here. Now, just like before, we had to figure out what x is to plug it into y to figure out what y is to determine the height. So again, we had to figure out, to get the height, we had to take your corresponding x value, plug it into the y to get the height, right? So you saw me do that many times. You plugged in the x to get the y, plug in the x to get the y, plug in the x to get the y, plug in the x to get the y. It's the same thing here. It's the same exact thing here. What is my x so that I can get my y? What is my x so that I can get my y? So this is me doing it here. I'm going to plug in my x, I over n, to get my y. So the function in this case is x squared. So you're going to plug I over n into x squared. And that will give you the y. Remember, everything's generic here because we have to let the rectangles go to infinity. But this is where you plug the x into the function. If the function is the square root of x, then I'm doing the square root of I over n. Like, you have to plug it into whatever function you have. And then, so it's the function times x sub I times delta x. And delta x we had already decided was 1 over n. So that's where this 1 over n is coming from. It's the delta x. It's the length times the width. Length times the width of one rectangle. So we plug this in to find y. So now I have the length times the width. The length times the width. If you just need me to reiterate, this is the length of, this is one rectangle. The area of one rectangle. This is the length. This is the width. So it's the area of one rectangle. This is adding up all the rectangles. This is letting the rectangles go to infinity. So right now we're just figuring out what does the area of one rectangle look like. Now you want to do the algebra on this part, okay? So you want to square this. So I just write underneath for a moment so you can, so I don't have to write everything 101 times. I squared, you have I squared over n squared. And then you have to multiply that times 1 over n. So I squared over n squared times 1 over n is I squared over n cubed. Now, I tried to explain earlier that when you have a constant, and I don't have it in front of me, but if you recall earlier, I had something like 2 times I. So when you have a constant, you want to, sorry, I'm not saying the word I want to use. When you have a multiplier, that just is going to make whatever it is something that many times bigger or smaller. If it's a 1/2, it'll make it smaller. So when you're doing this part here, the variable is actually the I. For sigma, this is really important. This will confuse you if you don't get this. The sigma, the variable is I, because I is going from 1 to n. I is changing. When you do the limit, the variable is n. So for this part, I squared is what's significant. The n is a constant. Like if this goes from 1 to 10, this is 10 cubed or 1,000. This is a constant here, 1 over 1,000, but this is the constant. So you don't have to write it like this. I just want to write it because I want to make it really clear to the students who's like the big player, the heavy hitter right now. And it's the I. So the 1 over n cubed is actually a constant for sigma. So you could sort of think about it like this. I is going to be the heavy hitter, not the n. That's just going to multiply times whatever this is here. So now everything in this type of problem is very abstract. So now we're going to come over here to where your formulas were. All right, so formula for I squared is this thing right here. So you're going to notice I'm going to replace this is equal to this. Make sure you understand what I just said. This equals this. These are equivalent statements. I could either crunch this out by hand or plug it into this. They will both give me the same answer. So you're going to notice that I'm going to take all of this and replace it with its equivalent definition. All right, so this equals this. I hope you're all with me. This equals this. So I replaced this with this. Now, at the very end, and I mean we are really full circle here, at the very end you're taking a limit, right? We learned this day one in calculus, how to do limits. So try to think about what kind of rules you would use. Like if I put this on test 1, you would all know how to solve it. It's just that it's sitting here in this section that you might be like, what the heck is this? What is she doing? Let me just rewrite it a little bit nicer. If you're finding this extraordinarily painful, it's about done. But I hope you're finding it interesting. I mean, you guys really have a huge amount of math skills by the time you get to calculus. I mean, way above the average person. It's very impressive. All right, so if I had put this on test 1, you guys would have done this very easily. So the first thing you would have said, okay, Professor Whelan, is a fraction going to infinity. If it's a fraction going to infinity, you have to use the top heavy, bottom heavy, or equal in degree rules, right? So the first thing I have to figure out, well, what is the degree of the top? Well, it's going to be an n times a 2n. Like, I don't want to FOIL all this out. That's a waste of my time. But if you just FOIL out the first times the first times the first, you'll get actually the first term of the polynomial. So the first term of this polynomial would be 2n to the third. The first times the first times the first will give you the first term of the polynomial if you FOILed it out. So if you notice, did I write it right? I wrote a 3. I can't read my own handwriting. Okay. Oh, and I changed this. I'm sure you're all screaming at me going, Professor Whelan, you changed this. All right, let me fix it. So it's a 3. So you're looking at this and you're going, okay, it's degree 3 over degree 3. So if it's equal in degree, it means it's the ratio of the coefficients. Well, here's the ratio of the coefficients, 2 over 6. 2 over 6 is the ratio of the coefficients, which reduces to 1 over 3. So what is 1 over 3? Well, 1 over 3 is the exact area under that curve. The exact area under this curve is 1/3 units. That's it. You've found the exact area. Now put it together. The exact area is 1/3. Can you see? Right? That's 0.333333 going on and on and on and on, right? Can you see how that fits? Can you pull it all together and see what we did there? Okay? I know you're going to have a lot of questions on the homework. I'm totally cool with that. Just throw them at me, okay? All right. I will probably just want to do one quick wrap-up video after this. I'll catch you. Bye-bye.